Hey, welcome back. All right, I skipped activity 4, 5, and 6 because they're easier to do in a lab. So I am here at potential energy. I guess it's not really an activity number. I'll call it 6.5, maybe 7. 7 would probably be better. All right. So a charge is moved along the indicated path. For each case, specify whether the change in potential energy is equal to, greater than, or less than 0. Indicate if the potential difference between the initial and final points is, okay, so we got to determine voltage and potential, okay? And then we need to make sure that our answers are consistent. Okay, that makes sense. So I'm going to start by writing down a couple formulas. So we have V equals negative integral E dot ds. And therefore, we're also going to have E equals negative divergence, basically the derivative of voltage. Okay. Yeah, let's go for that. We'll start with those two. Okay. So, as always in life, when I have a electric field like this, I always make sure I draw it as a plate charge on both sides. An infinite line of charge. Okay? Yeah, that's good enough. All right, so for this guy, we need to find what? Change in potential energy. So change in potential energy is going to be 0. Because potential energy here is energy due to position, and since it is moving perpendicular, so potential energy is measured in joules. So one of the formulas we could have for determining joules put a Q here, there we go, would be work equals F dot ds. We know that force then can equal E times Q, where Q in this case would be constant. So then E dot ds, where this dot product is, the magnitude is determined by cosine of theta. Well, in this case, the theta between the electric field and the motion is 90 degrees. Cosine of 90 degrees is 0. Therefore, work done is 0. Therefore, change in potential energy is 0. Okay, so now let's find the voltage. Well, I'm going to find the voltage by, okay, so we won't know the voltage per se because there's a C involved here, but we will know the change in voltage. So the change in voltage is going to be 0 because the electric field at this point will be the same as the electric field at that point. Is that convincing? I know it's totally true. I just want to make sure. Yes, I'm going to say it is. Because E dot ds right here, that equals 0. So the integral at most can equal a constant. And then when we take that constant subtracted from each other, it's going to end up being 0. So change in voltage also equals 0. All right. Now onto this guy. Now, I just wonder if I could copy and paste the electric plates, but that's probably more trouble than it's worth. All right. Charged plates. There we go. All right, so now this time we have a particle, a negative particle moving away from the positive side. So if you think of it, there's attraction between these, so I'm going to draw a little spring here. Don't actually draw the spring on the lab assignment, but I do because it makes it more sense. So now, so tasty. So as we stretch the spring, we're going to create more energy. So change in potential energy will be greater than 0 because we're stretching the spring. When we let go, it's going to then bounce back. So we're storing energy by moving this particle. Okay? So now voltage. So so work, which is pretty much the same as potential energy, equals V times Q. This is the whole reason we have voltage. It's a potential of potential energy. And that the first time I said potential, I'm talking about the potential based on the amount of Q we have, amount of charge. So the way I'm going to look at this then is if we have delta U as positive and we have a negative Q, then the change in voltage is going to be negative. Okay? Seems reasonable. Let's look at this from a different way too. So moving it up here, we create some. So the particle naturally wants to move this direction. No, it doesn't. This is moving opposite. We're pulling it. Okay, so what they're looking for here then is they're looking for you to know that when you have a negative charge, the difference in potential energy will be different than potential. And the reason that is because part of the assumption, the definition for potential, is the joules per coulomb required to bring a test particle that's positive from infinity to whatever point you're looking at. So when you're saying, so then you're talking about a negative particle and potential energy, that then ruins the assumption of positive test particle. So then you have to use the idea of it being negative. So I think that's all they're going for between the difference between part A and part B. So for example, for these three, the potential energy and change in voltage will all be the same, greater than 0, less than 0, while voltage will be different. So, and if you want to look at this just in terms of, because I'm not really quite sure what they are asking for here, because indicate if the potential difference between the initial and final point is, you know, this or that. So let's call this guy 1, let's call this guy 2. So is the difference in this case V1, 2, which equals V1 minus V2, or is it V2, 1, which is V2 minus V1. So maybe there's a right answer there. Maybe I'm just not mathematically savvy enough. That's okay. I'll move over it. Get over it. But the concept here is if we took a test particle that was positive, moved it to here, it might take us 9,004 joules. We took a same kind of particle, moved it here though, well, we'd be moving it further away from the positive, so it would be easier to move it closer to the negatives. So this might only take us 9,002 joules. So the potential V here is greater than the potential V there. So when we say it's negative, they probably want us to do V21, which would be V2 minus V1. So the final minus the initial. I'm assuming that's what they mean by difference. So that's the answer I'm going to go with. So, and if you got in a test, I would just go with that assumption there. All right, next guy. So again, draw our little parallel plate capacitor, positives and negatives. Oh, got one right up there. I can't quite reach it. That's okay. Don't care. All right. So one of the things we know from earlier is this is a dot product, E dot ds. So the only part that matters is the part that is parallel to the electric field. So we could redraw this as vectors, where this part would be 90 degrees perpendicular and therefore not matter. So the voltage change will be this, or energy change is going to be the same for this section as it is for that section. So change in potential energy. So we're taking a positive particle and we're moving it towards other positive particles. So we're going to be adding potential energy. We're putting more potential energy in. Potential energy at this point will be higher than the potential energy at that point. And for voltage, so voltage, since it's a positive particle, it'll be the same. We'll also have greater potential energy once we get it there. All right? This guy goes with the idea of a conservative field. So here, potential energy is energy due to position. It ended in the same position it started with, therefore 0. No energy expended. Yeah, tell that to someone who runs races for a living, i.e. not me. All right. And change in voltage then will also be 0. Bam, easy, because it's a circular path. All right. Now this is the first one where they give us, which is not circular. Or not, they're not straight, not all parallel. So I'm going to assume we could draw another like half electric field line right in the middle, right there. So it's this distance that matters because it's going to be perpendicular to assumed equal potential lines, like this. All right? So we are moving it away from positives and towards negatives, which is the way it wants to go anyway. So we're going to be converting some potential energy to kinetic energy. So potential energy at the final location will be less than 0. And then change in voltage will be also less than 0 because it's a positive charge, and work, which is pretty much the same idea as potential energy, is voltage times charge. Charge is positive, so the sign stays the same. All right, so we have a shell of negative charge as shown. So these are all negative charges. So since we have negative charges in a spherical shell, they're all going to cancel out and create no net electric field on the inside. So there'll be no net electric field. So change in energy will be 0, since there'll be no net force then on the charge. And there might be a potential inside, but the potential difference, the difference between 82 points, will be 0. All right, and that's all for the shapes. Now we're moving on to, man, these guys could be whole new activities. All right. So sweet, so sweet. A small charge of Q equals 0.33 millicoulombs and mass equals this is initially at rest above a large sheet of charge. Okay? A short time later, it is observed to have moved away from the sheet a certain distance and to have a speed of 2,000 meters per second. What is the charge density? Neglect gravity. All right, so we take a small supercharged BB. We have a so we have a plane of charge. This plane of charge is, they don't tell us. Well, okay, so we have a negative charge and it repels it, so I'm going to say it's negative as well. So we have a negative, creates a field, electric field. I guess the electric field's going downward because negative charges are sinks. We have a little BB right here with negative point, so we're going to say 0.33 times 10 to the negative third coulombs and 3 times 10 to the negative third grams. So I'm going to call that 10 to the negative 6 kilograms. Okay? And it starts at a distance of 2.5. So I'm going to say it starts at 0 and it ends up at 2.5. So this is going to be 2.5 times 10 to the negative second meters, and the speed is going to be 2,000 meters per second. What is the charge density of the sheet? All right. So the idea here is going to be conservation of energy. So it's going to start with potential energy due to position, and it's going to convert some of that potential energy to kinetic energy. So to do this, we're going to start by looking, we want the potential, because potential is what gives us energy. So we have potential equals negative integral E dot ds. We know that the electric field is sigma over 2 epsilon naught ds for a infinite plane. Like, what? How do you know that? I don't really, I just guessed. Well, I've seen it before, so I might be remembering it right, I might not. So we're just going to Google. Hello, Google. Let's do electric field of an infinite slab. Slab sounds much more manly than plane. MIT.edu, why are you so slow? Never mind, you failed me. Where's hyperphysics? I gotta do infinite plane, infinite sheet. Ah, see? Thank you, hyperphysics. Really, hyperphysics? Unavailable? Unavailable? You're killing me. There we go, finally. Electric field equals sigma over 2 epsilon naught. There we go. So I am right. See, why do I even look this up? I should not doubt myself. All right. So the big thing with electric sheets is that it's in uniform, which is why parallel plate capacitors work so well. So we can, by uniform I mean constant. I'm going to call this direction x. Change the s to x. That works too. Therefore, we take the integral of nothing. We get whatever the something is that we're integrating by. So it's going to be negative sigma over 2 epsilon naught times x. I'm going to multiply this by 1 over 2 pi. So 2 pi over 2 pi, which is 1. But that gives me 1 over 4 pi epsilon naught on the bottom. And the reason I wanted 1 over 4 pi epsilon naught on the bottom is because then that just gives me k, negative k sigma x times 2 pi. Okay? So now that I have all this great information, so I'm going to say that potential energy equals voltage times Q, which in this case is negative k sigma x 2 pi. God, it sounds like such a party with so many people coming. Times 0.33 times 10 to the negative third times, nope, that's all we got there. Bam. All right, and then we're going to say that this equals, now we're going to use 1/2 mv squared, straight from physics 1. 1/2 mass, 3 times 10 to the negative 6, and then 2 times 10 to the third. 2 times 10 to the third squared, 1/2 mv squared. All right. So x here is how far it's traveled. So 2.5 times 10 to the negative second. So really here, I should have done limits of integration, and it have been from 0 to x, how far it's traveled. So I should be subtracting a 0, but I'm not going to subtract the 0. Okay. So now we're solving for this guy right there. So sigma equals, let's do some canceling. 10 to the negative third. That'll cancel. one of the 10 to the thirds will cancel. The other 10 to the third will still be there. So let's see here. Sigma equals 3 times 4 times 10 to the third over 8.99 times 10 to the ninth times 2.5 times 10 to the negative second times 0.33. Let's see, is there anything else I can easily cancel? Maybe. So we'll do this. That becomes 7th. Move this up here, comes 10 to the negative 7th. These guys become 10 to the negative 4th. This guy moves over, becomes 10 to the negative 2nd. Move it up here, becomes 10 to the 2nd. Cancel these, comes 10 squared. This is terrible boardsmanship. So we have 12 over 9, maybe. That's terrible. 2.5 times 33 times 10 to the squared. Man, I might be way off on this. I'm still going to try, of course. But we're going to see. So I'm going to do divided by 9 times 2.5 times 33. Boom, 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 boom. And we get 1.6. Maybe. 1.6. And that would be coulombs per meter squared. That seems reasonable enough. Maybe, not really sure. Alright, but that's at least the idea. So, I'm going to claim partial credit for that. You should probably be more careful than I was, though. I'm quite cavalier. And, since we know it's negative, we have to make sure we have the negative in there as well. I probably dropped it somewhere along the line. Alright, and that's how you do the first part. Alright, probably going to do the same idea here. So, for number 3, an electron is initially 2 centimeters from a proton and is then given an initial velocity v away from the proton. If v is 91 meters per second, how far does the electron move before it is momentarily stops? How fast would the electron have to be launched in order to escape from the proton, i.e. never return? Sounds ominous when you say that. Okay, so we have an electron. Draw a little picture up here. So we have a proton, and we have an electron, and it's launched this direction at 91 meters per second. And we want to see how far does it get. Is there an initial distance between the two? 2 centimeters. Two times 10 to the negative second meters. And then we have, let's see, mass equals 9.1 times 10 to the negative 31st. That's mass electron. Yeah, let's go for that. All right. So this, again, it's just going to have to do with energy. So, let's find the potential for the first part. So potential, using 2 point charges, is kq over r, which equals 8.99 times 10 to the 9th. Q in this case will be the proton, which will be 1.602 times 10 to the negative 19th. And the distance will be 2 times 10 to the negative second. Okay? Okay. Cleaning this up a little bit. 10 squared up here. 9 plus 10 to the negative 9th is 10 to the negative 10th. 10 to the negative 10th plus 2, or times 10 squared, will be 10 to the negative 8th. So we have 8.99. 8.99 times 1.602 all over 2 times 10 to the negative 8th. I'll get, do I want an answer yet? Maybe not. All right. So now that we have that voltage, we can find the potential energy it has to start with. So when the proton stops, so it starts with potential energy at this point over here, potential energy right here. And then it converts it to kinetic energy until it gets to this point here, distance d, where all the potential energy has been converted to kinetic energy. Now, totally backwards. So it has kinetic energy here, converts it to potential energy here, and then at this point when it's all potential energy, kinetic's gone, and then it falls back. Got it. All right. So we need a voltage difference between point 1 and point 2, where this will be point 1 and this will be point 2. So delta V will specifically be, I'm just going to redo this part real briefly right quick. So we have 8.99 times 10 to the 9th times Q, which is the proton, 1.602 times 10 to the negative 19th. And then we're going to do it between 2 times 10 to the negative second and 1 over d, where d is the distance. Got it. And then we're going to set this all equal set this guy equal to the kinetic energy that we initially had, 1/2 mv squared, which we know it's going to be gone. All right. So then we got a mass, we have a velocity. Now we just need to simplify this guy. Simplify and solve. And then we're going to also have to convert this guy up here to, there we go, to an energy as well. There we go. Excellent. So the potential energy here equals Q times delta V, which is this guy, where this is going to be the Q of the electron. And then that'll equal then 1/2 mv squared, which was the kinetic energy, which we initially started with, but then we converted over to completely potential. Okay.